we left off last time. Well, we talked about this. We said we're going to use this basic model here at the bottom a lot. It's got a generator, it's got a transmission line, it's got a load. And we talked about what this could represent, like what things could be a generator circuit, what things could be the load circuit, what sorts of things could be a transmission line. And the takeaway from this is just that we're going to use this generic model, but it could actually represent a ton of different situations. So we're keeping it generic so that it can apply to a lot of different things. And then we wanted to answer the question of, well, how come we didn't pay attention to this in like 240 or 340? Well, we're going to talk about that today. Sometimes you can ignore the effects, sometimes you can't. How do you know? We're going to have a rule. You're going to be able to just kind of check the rule and be able to figure it out. So last time, our main thing we said on this slide was, well, at the end of the day, it's going to depend on this ratio, where L is the physical length of the transmission line. So you got some cable. It's like you literally get out your ruler or your measuring tape. Like, how physically long is this in meters? And lambda, well, lambda, we've already seen the equation for lambda. Lambda is just UP divided by F, where F is the frequency, UP is the speed of the wave in meters per second. Okay. So I think we left off here the last time. And what we're basically talking about when we ended was, we are saying, let's assume we have a voltage source and it's a sinusoidal voltage source. And its equation is this simple thing down here. It has some amplitude, V0, so that's its amplitude in volts, cos omega t, where omega is just 2 pi times the frequency in hertz. So it's just a regular old cos wave, okay? So this is actually an instantaneous voltage. So it depends on the time. VAA is the voltage at the input of the transmission line. VBB is the voltage at the output of the transmission line. The effect of the, or I guess I could say, whether the transmission line effects are important or not depends on the time delay of the wave, because remember, we've got a wave and it's traveling down here. It takes some time to get from A prime to B prime. It can't travel instantaneously. The fastest it can travel is the speed of light. So the effects are going to depend on how long that delay time is, which is really, you could think about, instead of time, you could think about it in terms of a phase shift. So if we want to figure out what is VBB prime at some time t, well, it's going to be VAA prime at some prior VAA, okay? So VAA at some point in the past. Now, I'm going to write it down. It's L over C. We'll talk about why it's L over C. So this, I'm going to call that like some delay, like T prime or something like that. And what we're saying here is that, let's say the wave is at a certain point at AA prime. Well, it takes a certain amount of time to get the BB prime, or equivalently, if you thought about what is the wave at BB prime, well, it's the wave at AA prime at some point in the past. So if it takes like 3 seconds to get from AA to BB, the wave at BB prime is whatever the wave at AA prime was 3 seconds ago. Okay. So to get that time delay, well, it's just a regular old time delay. It's like You're on the 405 driving at 65 miles per hour. That's your speed, that's UP. And you wanna think about how long is it gonna take you to drive a mile? So L is like a mile, T prime is how long it's gonna take to get there. So you would just rearrange this. You go T prime equals L over UP. And we're assuming UP equals C here. We can't always assume that. So UP is whatever the speed is. Sometimes it's C, but you can't assume it's always C. It can't be more than C. So it's either C or it's less than C. In our case, we're assuming it's C. So our time delay to get from AA to BB is L over C. So the voltage that we're seeing at BB prime is the voltage we saw at AA prime, L over C seconds ago. So then we could plug that into our equation. So what do we got? We got VBB prime at T equals, so we have to plug this in to T. So that can get plugged into T. Because this is VAA at T, but we're saying VBB prime is VAA not at T, but at T minus L over C. Okay, so what do we got? We got V0 cos omega times T, and we said the T is actually T minus L over C. Then we can multiply that through. So that would be V0 cos omega T minus omega L over C. I'm going to call that phi 0. So phi 0 equals omega L over C, and it's going to have units of radians. So it's a phase shift. So at the beginning, when we did this T prime business, that was thinking about it in terms of a time delay. When we write it in terms of omega L over C, we're thinking about it in terms of a phase shift. So if there's a significant phase shift between the input and the output of the transmission line, we have to worry about transmission line effects. So let's keep thinking about this. So we've got our phi 0 here, right? Omega L over C. So we are going to take two cases. We are going to say, imagine you are in the lab. You are in a circuits lab and you're doing breadboard stuff. And on the breadboard, you need a wire to plug in from the one pin to another pin. And so you go over to the spool of wire and you got your wire cutters and you cut off a 5 centimeter piece of wire. That's about 2 inches. It's not that long. It's pretty short, right? So you chop off a 5 centimeter piece of wire, you strip off the ends, you stick it into your breadboard, and we're going to compare it for 2 different frequencies. Let's say you had your signal generator set to 1 kilohertz. We're going to look at the effects of the transmission line. Let's say we had the same wire, same 5 centimeter wire, but we were using a frequency of 1 gigahertz instead. So 1 kilohertz is typical low frequency stuff that you use in your circuits labs. 1 gigahertz is typical of a frequency that you might use for your cell phone, okay? So in your cell phone, there are circuits that operate at around 1 gigahertz. There's printed circuit boards that have transmission lines on them that have a signal at around 1 gigahertz. The wires or the traces on the circuit board might not be 5 centimeters long. They might be, I don't know, maybe 1 centimeter or less, but this will give you an idea of the difference between 1 kilohertz and 1 gigahertz for the same wire. To make our life easy, let's assume T equals 0. What does that mean? Just means we're choosing a reference time where it's like we have our cos waveform And we're choosing like a time like right there. This is t, so that's t equals 0. And we'll choose that time so that we're at a peak right here at a prime. So if we look back here, v0 cos omega t. So if we make t equal to 0, omega times t equals 0. The cos of 0 is 1. 1 times v0 is v0. So va a prime just equal to 0. That's what I was saying, that we're at a peak right there. We're at a peak at a prime. Because it's just a time domain waveform. It's going up, it's going down, it's going up, it's going down. And we are just analyzing the point at which it's at a peak at a prime. And we want to know, well, when it's at that peak at a prime, what's going on at vbb prime? And we just found an equation for it. So we could use this equation. But we said t equals 0, right? So t equals 0 wipes out the omega t. So we're just left with the v0 cos minus phi 0, which is minus omega L over C. Okay, so VBB equals V0 cos minus phi 0, which equals V0 cos positive phi 0. Because remember, cos is an even function, right? It doesn't matter if you did that minus sign or not, you'd get the same thing, all right? Just nice to have one less negative sign. And this is V0 cos phi 0 is omega, which is 2 pi f. So I'm going to keep writing that because I hope to kind of drill that into your mind. So as soon as you see omega, you just think 2 pi f. So it'd be the cos of 2 pi f, that's omega, and then L divided by C. We know F, it's 1 kilohertz. We know L, it's 5 centimeters, and we know C because it's a constant. So what does this equal? It equals V0 cos 2 pi times 1, I'll just say 10 to the 3 because that's 1,000, right? Because it's 1 kilohertz. L is 5 times 10 to the minus 2. And C is 3 times 10 to the 8. Now, you have to have your calculator in radian mode. Whenever you have a 2 pi in the equation, that's normally a sign you're in radians. You got to be in radians. So can someone, so Rubina got 3 times 10 to the minus 7 is my phi 0, fair enough. And then you need to do the cos of that. And what do you get? Rubina says almost 1. Does anyone get 1 or something almost 1 or?
I got 1.
You got 1. So depending on your calculator, it might be perfectly 1. If you have maybe more digits on your calculator or use MATLAB or something like that, you get something like V0. Actually, I think I was skimpy on the 9s there. I think there'd probably be another 2 or 3 9s. Think about how close that is to 1. It's incredibly close to 1. It's ridiculously close to 1. Meaning that when you're at the peak, at the input of the transmission line, you are ridiculously close also to the peak at the output of the transmission line. Meaning, whatever the input is at the output, for all practical purposes, the time delay is negligible. The phase shift, negligible. You can ignore it because it's so close. So let's do the same thing, but at 1 gigahertz. So VBB prime equals the same thing, So it'll be V0 cos 2 pi, and then 1 times 10 to the 9, because it's 1 gigahertz. The length of the line is the same. All right, someone punch that in. Tell me what you get. Remember radian mode. So grab your calculator, go 2 times pi times 1 times 10 to the 9 times 5 times 10 to the minus 2 divided by 3 times 10 to the 8. Then you do cos of that answer. And what do you get? Anybody?
I got 1.047. 1977.
For what's in the parentheses?
Correct.
Then go, if the yes, then just go ahead and cos that. Marita gets half. Anybody get the same as Marita?
I got half as well.
Half. Yes. Equals 1/2 V0. This means when you are at the peak here, you are only like halfway up the peak. Like if that's the peak up there, if your amplitude, if your V0 is 1 volt, when you're at 1 volt at the input, you're at 1/2 volt at the output. This is not good. You need to worry about this. The voltage is not the same. There is a phase shift. There is a time delay. And because of this, you have to treat it as waves traveling on a transmission line. And potentially, if you have waves, you can have reflections. And if you have reflections, you can have an interference between the incident wave and the reflected wave. So that's a preview of where we're heading with all of this. And all of it comes about because of these time delays, these phase shifts that we have to worry about. So how do we know, like, what is our rule going to be? Okay, our rule, as I said, it's going to be based on L divided by lambda. So this is what we had for our phi 0, right? That's how we defined it. And then as always, we can just say, well, omega equals 2 pi f, right? So that's where that comes from. And then if we liked, we could say, well, for UP equals C, which is our case here. Our velocity is the speed of light. We'd have C equals F lambda. And we could solve that for F divided by C. So if we rearrange that equation for F divided by C, what would we get? Well, we'd bring the C over, but then we have to bring the lambda. It'd be 1 over lambda. So we can replace the F over C with 1 over lambda. This is how we're going to determine if we need to worry about transmission line effects. If L over lambda is really small, we can ignore them. Our dividing line is going to be this. It is not black and white. It is all shades of gray. But we are just going to go with a specific number. What is this number and like why? What's special about 0.01? Nothing really, but look at this. If that ratio is 0.01, that's kind of our border between don't have to worry about them, have to worry about them, okay? 0.01 is 1 over 100. 1 over 100 is 1%. 2 pi is a full cycle. It's like 360 degrees, right? So our dividing line is like 1% of a full cycle. It's like 3.6 degrees or whatever 2 pi divided by 100 is, okay? Pi is 3.14, so 2 pi is 6.28, and then you divide that by 100, so it'd be like 0.0628 or something like that, okay? It's 1% of a full revolution. So it's just a convenient kind of rule of thumb. It may be that the effects really aren't that major at only 0.01. They may not get that bad until 0.1 or something like that, but this is what we're going to use. When it's bigger than this 1%, we're saying, well, the phase shift due to the time delay is getting significant. So we need to take it into account because, as I said, we could have reflected signals that can get bounced back and cause problems for us. And we're going to look at that in a lot more detail. So it is not uncommon at all to have a question on a quiz, a midterm, or a final exam where you are asked, here's a situation. The transmission line is so, this long, the frequency is this. Do you have to worry about the transmission line effects or not? That's a pretty common question. And to answer it, this is what you do. You need to know L divided by lambda. Now, L is just the length of the line, right, in meters. Lambda is the wavelength, which you can solve from this equation. So lambda equals UP divided by F. Now, this is the general formula, okay? We didn't assume C for UP. So as long as you use the correct lambda here, you're good. These assume C. So this form with the C in it only works when the speed of the wave, UP, is equal to the speed of light. That's not always the case. You can't always assume that, okay?
So
As long
would
as you-
something like that be addressed in the question to
So
know
the way the question would normally go, it can take a number of different forms, but you probably wouldn't be just given UP and F, because then that's, if you're given UP, F, and L, then it's a little too easy, right? So what you might be given is some more information, like some of the properties of the transmission line. And we are going to have a formula shortly that allows you to calculate UP. So you could be told F and told something about the transmission line that should indicate to you whether it's UP is equal to C, or if you have to calculate UP using one of the formulas that we're going to get later this week or at the beginning of next week. Using that, you'd be able to calculate lambda, and you'd be able to figure out L over lambda. Another way you could get asked is you could be maybe given the information to calculate lambda, but then be asked something like, what's the largest length of transmission line that you could have before you start to need to worry about transmission line effects? So that's another way you could get asked that. Okay, so a quick discussion of dispersion. We're not going to deal with dispersion. You're not going to get asked any like numerical questions about dispersion. I just want you to have a feeling for what it is. So in that example we saw before with the 1 kilohertz signal versus the 1 gigahertz signal, both of those lines were 5 centimeters long, right? Imagine if the 1 kilohertz signal traveled at a different speed than the 1 gigahertz signal. Now, we're not talking about its cycles per second, right? So don't get confused with the frequency. Frequency is the number of cycles of the sine wave per second, which is different than how fast it's moving. Okay, we're talking about how quickly it would go down the transmission line from the input to the output. Okay, so it's different than the frequency. They're related, right? UP equals F times lambda. But lambda, that can change, right? All right. We've got a transmission line. I've just said the speed can depend on the frequency, which is a weird thing to think about maybe. If it does depend on the frequency, you have dispersion, you have a dispersive transmission line. This can become important, especially if you're dealing with like a high-speed digital signal. The easiest way to think about that is if you're like sending a 0, 1, 0, 1, 0, 1, right? Then it looks like a square wave, like this pulse train. If you have a dispersionless line, which means the speed doesn't depend on the frequency, the output looks the same. But if you have a transmission line that has dispersion in it, the different frequencies travel at different speeds. If you've taken a signal processing course, then you've probably done Fourier transforms and Fourier series, and you look at things in the frequency domain. So if you've got like power versus frequency, and you looked at a sine wave, it's an impulse, okay? At some frequency, I'll say like F0. That's all there is. Then the dispersion doesn't matter so much. But if you're looking at like a digital pulse train, like a square wave, square waves decompose into a bunch of different frequencies. So it's like, got another frequency, another frequency, another frequency, F1, F2, F3, right? And for a square wave, it's like one, if it was like a 1 gigahertz square wave, it'd be like the first component would be at 1 gigahertz, the second would be at 3 gigahertz, the next at 5, the next at 7, and so on and so on and so on. So your waveform is made up of a bunch of different frequencies. If they travel down the transmission line at different speeds, that means they arrive at the output at different times. Their phase relationship has gotten messed up. At the end of the day, what that looks like is a distorted waveform, which can lead to bit errors. Okay, so you can increase the bit error rate. Anthony?
Yeah, so does that mean the integrity of the signal has been lost? Is that another way to use dispersion?
Yes. Yep. That's another consequence of dispersion. Yep.
Thank you.
Yep. So it can distort things because different frequencies propagate at different velocities. So just kind of store that away, and maybe at some point in the future, you might need to worry about it. So now let's get into the good stuff here. We're talking about transmission lines, and we're going to start to now look at them in some detail. The types of transmission lines that we are going to look at are called transverse electromagnetic transmission lines. You don't have to necessarily remember that term, but what the term means and why you might remember it is because, first of all, for the word transverse, if that word's not that familiar to you, just replace it with orthogonal or normal, 90 degrees, okay? That's all that it means. So the electric and magnetic fields are going to be transverse to each other, but they're also going to be orthogonal to the direction of propagation of the wave. This is what a transverse electromagnetic wave is. And there's certain types of transmission lines that support, that allow, that have transverse electromagnetic waves on them. And the coaxial line is one of them. Okay, so let's look at this coaxial line. What do we got? Center conductor. What is that thing? Well, it's going to be metal. It's going to be metal in the shape of a cylinder. The cylinder goes through the middle of this thing. How big is that cylinder? Well, it depends on the type of coaxial cable, but it's going to be pretty small. Like if you've ever looked at in the end of one of these things, you know, it's like, I don't know, a millimeter in diameter or something like that. It's not that big. Okay. So there's the cylinder, goes all the way through. It's usually made out of a highly conductive material. Maybe it's copper. Maybe it's solid copper. Maybe it's strands of copper all kind of bunched together. Okay. But it's a metal. This green stuff in the middle here, that is not a metal. That's the opposite of a metal. That is an insulator or a dielectric. We do not want that to be able to conduct electricity. We don't want current just kind of like going like bang. I'm just going to go like kind of like straight up or down. We want the current to go along the center conductor and then have the outside as the return path. You can also think about the outside as ground, so that you often hear coaxial lines referred to that way, that the outer shell, which is this part all the way around the outside, which is another metal, you could think about that as ground. Okay. Okay. So we got two metals and we've got an insulator in between them. We got a voltage source. The voltage source, sinusoidal, because all we're looking at is sinusoidal voltages. It has some internal resistance. Maybe it's really, really low and you could almost ignore it. Maybe it's 50 ohms. Maybe it's high. Maybe it's 1 kilo ohm or more, right? Connected to the center conductor. That center conductor runs all the way through the middle. Here it's connected to some load on the other side, and the other side of the load is connected to the same place as the other side of the generator. Now, if we look at the end of this coaxial cable, so we're looking at the cross section. So the line is like going into the screen. Okay, it's like that. You can see the green lines and the red lines. They represent the magnetic field and the electric field. And if you look at any point, like there's an obvious one, but you can look anywhere. The green is orthogonal to the red, 90 degrees. The red, the electric field, always points directly from the one conductor to the other conductor. So you can see it's kind of pointing directly outward in the radial direction, where the current is going around in loops. So currents produce magnetic fields. Magnetic fields are always in closed loops. And if you want to know what direction the magnetic field is kind of encircling in, or direction it's going, you put your thumb in the direction of the current. So if the current's going into the screen, you take your right hand, you'd put your thumb into your screen, and you would look at the way that your four fingers curl. And so they curl in this direction. The wave is also into the screen. So you can see if the wave is going into the screen, the direction of propagation is orthogonal to the red one. So it's like that. It's a little hard to draw in 3 dimensions, but it's like that. Okay. So there you can kind of see how it's orthogonal to the red one. Same thing for the green one. In here, the dielectric, which I'm going to say more often than insulator, but dielectric just means insulator. The green over here is just white over here. So the fields, the electric and magnetic fields, exist in the dielectric. The currents exist on the conductor. The voltage is between the conductors. Here are the transmission lines we're going to look at. We are only going to look at TEM lines, which is a little bit of a lie because this one's actually called quasi-TEM, but you don't need to worry about that. We're going to look at the coaxial line. That's the one we've been talking about. Metal cylinder in the middle, metal shell all around the outside. Over here, this is like, we have like X-ray vision or something like that. Like you can't normally see this, you know, through it to see the center conductor. Normally it's just all covered around the outside. So we have two metals and we have a dielectric in the middle. Note these are these symbols, these letters that are defining our dimensions. 2A is the diameter of the center conductor. That means A is the radius of the center conductor. And very shortly, we're going to have equations for coaxial line, and they're going to have A and B in them. It's a very common mistake for students to mix up radius and diameter for these types of problems. The second type we're going to look at is called a two-wire line, and it's got a lowercase d in it, which is the diameter. And we're going to see equations shortly with lowercase d in them, but it means diameter. So I want you to be kind of paranoid and always asking yourself, in this equation, does that letter represent radius or diameter? And in this question, did they give me radius or diameter? Especially on the quiz every single semester, I get a number of students who email me and they say, I keep doing this question. I keep getting the wrong answer. I think Canvas is wrong. And it's not. It's an error of using the radius instead of diameter or the diameter instead of the radius. So just kind of really let that sink in. All right, here for this 2-wire line, we have 2 wires and they're parallel. They're separated by a distance capital D, and that's center to center. But in some cases, it'll give the separation between the wires and it's a little ambiguous. Any questions on an exam, I will be clear about this, right? Because if a question just said the separation between the wires is 1 centimeter, then you'd be wondering, does that mean D equals 1 centimeter? Or does that mean that equals 1 centimeter? It's going to be different by 2 radii. So it's going to be off. The difference is going to be 1 diameter. In the equations, it's capital D. And that is center to center. Okay. But I think on the quizzes, it might just say the separation is blah, 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 and not take into account the radii. But any exam question, I will be sure to be specific about that. So that's our second line. Question? Was there a question? No? Okay. The third one is a parallel plate line. So this one is a thin sheet of metal, W wide, then a dielectric or insulator that is H high, and then another thin metal layer that's also W wide. It's like a parallel plate capacitor. This is one of our transmission lines. Strip line is an important type of transmission line that's used all over the place in industry. We're not going to look at it in detail. It's basically the parallel plate line with another, kind of less wide line in the middle. If you go on to take other courses like maybe ECE 572, then you might use this one. We are going to look at the microstrip line. So this has some thin trace. This is normally like on a printed circuit board. It's W wide. Then we have a substrate, which is our dielectric, our insulator. It's H high. And then we have a ground plane, which is just a big area of thin metal on the bottom. The last one is coplanar waveguide. We're not going to look at this one in detail, but it's another one it's commonly used. It's just a little more complicated to look at. Note that it has 1, 2, 3 conductors on the top, and potentially you can also have this without the one on the bottom. So it has 3 or 4 different metals. This one, 2 metals. This one, 2 metals. 2 metals, 3 metals, 2 metals, 3 or 4 metals. We are only looking at the 2 metal ones. These are the transmission lines that we will look at in detail and be able to solve problems for and be able to design. There's 4 of them. We're going to start off by looking at the top 3. Okay. And then later, maybe next week or the following week, we'll get to the microstrip line. There are lots of other types of transmission lines, 2 of the most popular of which are shown here. We have a rectangular waveguide, which is actually, it just looks like a pipe. Like it's just a metal, usually rectangular, but can be circular, pipe that can be bolted to other waveguides. And the advantage of them is that you can have really low losses and it can handle high powers. But they only become practical in their physical size when you get above like, well, several gigahertz. And they're most commonly used like 8 gigahertz and up. Below that, they get to be really huge and heavy and bulky and hard to work with. If you want to learn more about waveguides, ECE 571, the follow-on course to this one, you will learn all about waveguides and how the electromagnetic waves propagate inside of them. Another type of higher order transmission line is optical fibers. So if you're wondering how optical fiber or fiber optic communications works, you can take a course. There are courses that go into detail on this, fiber optics, but it's a little more complicated. So we'll save that for other courses. We'll focus on the basics in here, which are the TEM lines, the 4 that we talked about in the previous slide. We need to model our transmission line. If we want to be able to come up with some equations and some conclusions about what is going on the transmission line, when these transmission line effects are important, we want to know, well, what is going to happen? So, like usual in engineering, we come up with a model for it, one that we can handle mathematically. And so we are going to do it first with this parallel wire representation. Now you might think, well, this is, I mean, it's just 2 parallel lines you drew there. Yeah. You can kind of see clearly how that would represent this one, right? This one is just 2 parallel lines. This dielectric, the green stuff in the middle, air is a dielectric. So if you like, you could think about that as air. And then you really just have 2 lines that are separated. But if you look at these other ones, like you can see how this one, well, this one is also just 2 lines separated, 2 parallel lines that are separated. This one also 2 lines that have a separation. And this one, a little harder to visualize maybe, but 2 lines that are parallel, like the outer shell is parallel to the inner conductor, and there are 2 lines. That's how we can represent any of those transmission lines by this parallel wire representation, okay? And it simplifies things. So if I've sold you on that this simple representation could represent any of those transmission lines because they all have 2 conductors and because they're all parallel, those 2 conductors are parallel, then we can take the next step where we just slice it up. Just like, boom, I'm just gonna slice up this line into chunks. So maybe your line is 1 meter long. And you're like, I'm gonna get a big long ruler. I'm gonna slice it up into chunks that are 1 centimeter long. So I have 100 sections, okay? Or maybe you did a millimeter. So you have 1,000 sections where each section, delta Z, is 1 millimeter or 1 centimeter long, okay? We're eventually gonna let delta Z go to 0. And so eventually we're going to treat them as differential sections that are extremely small. Okay, so basically, so far we said we're going to look at 4 transmission lines of detail. Each of the 4 we're going to look at has 2 conductors in it. Each of the 4 have the 2 conductors parallel to each other. So we're going to model it with a parallel wire representation. And we're going to break up that wire into chunks that are delta Z long, where delta Z is some physical length in meters. And then for each chunk, we are going to model the electrical behavior in that chunk by 4 circuit components. We've got a resistor. We've got an inductor. We got another resistor, and we got a capacitor. And you might think, well, why this set of components? Why a resistor and an inductor? And then why another resistor and a capacitor? Why are two of them in parallel and why are two of them in series? The answer is each one of these is representing a physical thing that will happen on the transmission line. And the easiest one to see that with, I think, is this resistor right here. So we said that, in our parallel wire representation, it's representing one of those 4 transmission lines. And each of those 4 transmission lines has 2 metals in it, 2 separate metals. Metals don't have infinite conductivity. They have some resistance. It might be really, really small, right? So if you got copper, you got a wire, just, you cut off some wire and it was copper, and you got your ohm meter, you had a multimeter, you switched to the ohm mode, and you put your 2 leads on the 2 ends of the wire. It might show 0, but if you got an accurate enough ohm meter, it would not show 0, okay? Because it would only be 0, perfectly 0 resistance if it was like a superconductor, if it was infinitely conductive. So if it said 0, it would only be because of the limitation of the multimeter, of the ohm meter, okay? Because there's got to be some, 1 milliohm or 1 micro ohm of resistance. And so every metal that makes up a transmission line is going to have a finite resistance associated with it. And that is being modeled with this resistor right here. Now, if you went into the lab and you cut off a 5 centimeter chunk, like we were talking about before, of wire, and you measured the resistance across that wire, and then you cut off a huge chunk of wire that was like, I don't know, 10 meters long, and you measured the resistance between the ends of that wire, well, there's going to be a lot more resistance across the 10-meter wire than there was across the 5 centimeter wire. So the value of that resistance is proportional to the length of that wire. In our case, it's proportional to the length of the section of wire, the delta Z. That's why we have a delta Z here. Azat, go ahead.
So you said it's proportional. Would it be, I don't say would it be fair to say, but if we take that 5 centimeter length of wire and compare that to 10-meter length of wire.
Yep.
Like my assumption would be that it would be linear. The resistance would be linear. Is it?
You're right.
Okay.
Yeah. And later on, we'll have an equation for that. Yep. And it's linear here as well, right? Delta Z, if you double delta Z, then you would double the total resistance, where the total resistance is R prime times delta Z, okay? R prime then, because this is a resistor, so the total value of this resistor should be in ohms. So we couldn't have just ohms for R prime, because then we'd have ohms times meters. We'd have ohm meters, which is not like a resistance value. So R prime, and this is the reason for the prime, it's in units of ohms per meter, which then gets multiplied by the meters in delta Z. So the meters cancel out, you're left with ohms. Now, you might not think about this before, I've thought about it, but just like there's a resistance in every wire, there's an inductance associated with every wire as well. And so for the exact same reason that we have this resistor here, we have this inductor here. More intuitive, I think, are these two. So note that they go between the one conductor and the other conductor. There's a capacitor and a resistor. So I think the easiest one to look at for this one is the parallel plate one. So it looks exactly like a capacitor, right? 2 parallel plates. So I think this one's obvious that there should be some capacitance between the upper and lower conductors, but all of them have 2 metals, right? So you could think about these as being like a capacitor between those ones. Same with the other ones. The resistor represents the finite conductivity of that dielectric. of the insulator. So these things are made of real materials. And so that might be incredibly high, the resistance value, or it might not be. And so we need it included in our model so we can handle a finite conductivity of the material that separates the conductors. They're all multiplied by delta Z, which means they're all per unit length value. So R prime, ohms per meter, represents the resistance in the wires. L prime, henries per meter. It's an inductance associated with the conductors. G prime. Now, G prime is an interesting one because this is the resistor symbol, right? So you would think, well, it's just a resistance. It's going to be in ohms. We could do it that way. But instead, we're going to think of it like a conductance, which is 1 divided by the resistance. It's 1 over ohms, which is Siemens. And because we're times delta Z, we have Siemens per meter, because then we were multiplied by the delta Z and the meters cancel out. And then we have the capacitance between the two conductors, farads per meter. This is our transmission line model. We'll eventually let delta Z go to 0. We'll get differential equations. And using those differential equations, we will see that waves exist on this transmission line. And if waves exist, we can potentially have reflective waves. So that's where we're heading with this. We're going to use this model to do all that. Okay. We have this very handy table, which you definitely want on your cheat sheet, which you can use to do the latest quiz that's been posted. You can treat these equations as if they are just handed down to you. We are not going to derive them right now. We will derive some of them by the end of the class, but we need to learn some more concepts and theories before we can derive these. So by the end of the class, we'll derive 1, 2, maybe all 4 of at least the coaxial ones. Essentially, if you're told it's a coaxial line, then you use this set of equations to calculate R prime, L prime, G prime, and C prime. If you're told it's a 2-wire line, then you use the middle set. If you're told it's a parallel plate, you use the last set. You need to be careful, as I said before, about your definition. So in the coaxial line, we have A and B. A is the radius because 2A is shown as the diameter. Same thing with B. Okay. The other ones have capital D and lowercase d. Here are our equations, capital D and lowercase d. In this case, lowercase d is the diameter. So if you use the radius in here, you're going to get the wrong answer. All right. So definitely want this table on your cheat sheet. Okay. So let's look at the coaxial one in some detail. All right. So we are looking specifically at this one. Okay. Although I guess what we're going to talk about here applies generally to the others as well. So let's look at the coaxial one though, just as an example. We have an RS. We've got an A, we've got a B. We already know what A and B are. A is the radius of the inner conductor. B is the radius of the outer conductor. All right, so A and B done. We just need to make sure we're dealing with radii, not diameters. What about RS? Here's our formula for RS. So if we look at RS, we've got frequency F in Hertz. So you can see that as the frequency goes up, the resistance RS goes up. And as RS goes up, R prime goes up. we also have mu C and sigma C. The C subscript means conductor. It means these parameters are material properties of the conductors, not of the insulating material. Mu is permeability. So this is the permeability of the conductors. Sigma C is the conductivity of the conductors. We'll do an example in a bit where we'll see this difference, but it's an important difference, and it's another place where lots of mistakes get made. All right, so as long as we're careful with our mu C and our sigma C, we're able to calculate RS. As long as we're careful with our radius versus diameter, we know A and B, we've got R prime. L prime. B and A, well, that's easy, right? So 2 pi is simple. The natural logarithm of B divided by A, radius of the outer divided by radius of the inner. What about this mu though? It's also permeability, but it's the permeability of the insulating material, the material between the conductors, whereas this one is the permeability of the conductor themselves. Every material has a permeability. Our transmission line has conductors and insulators. So we've got a permeability of the conductors, we got a permeability of the insulator, and you don't want to mix them up. The conductor properties only appear in RS. That's it. That applies to this one, it applies to this one. RS is the only place where the conductor properties come in. Everywhere else, mu, 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 sigma, 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 epsilon, epsilon, epsilon. All of these don't have a subscript, which means they are all the properties of the insulating material, not the conductor. So we would just need mu of the insulating material. And we've got L prime. As long as we know the conductivity, sigma, of the insulating material, then we've got G prime. And as long as we know epsilon of the insulating material, we know C prime. Okay. The other ones are very similar, right? They just have different geometry parameters. Like this one's got D's in it instead of A and B. But what I said applies for all of them. Like that mu, that sigma, that epsilon, that's for the insulating material. Just look for the subscript C, right? That tells you it's conductor. And you can assume it's not the conductor, it's the insulator if there's no subscript C. Okay, so we've pretty much gone through all this. This is the R prime calculation. The only thing I'll point out is that what if you had a really, really high conductivity of the conductors? That would mean sigma C is really, really high. Well, that would make RS really, really small. And if RS was really, really small, that would make R prime really, really small. So sometimes as an approximation, we'll say you can assume perfect conductors, or you can assume infinite conductivity for the conductors, or you can assume a lossless transmission line. That's basically telling you R prime equals 0. Even if sigma C isn't super, super high, if you looked at this ratio, F times mu C divided by sigma C, if that number is really, really small, that also means RS is going to be really, really small, which is going to make R prime really, really small. So that's R prime. L prime, we already went through this. We just need to make sure that we are dealing with the mu for the insulating material. G prime, sometimes we will say that the dielectric or the insulator has 0 conductivity. It's a perfect dielectric or a perfect insulator. That means the conductivity is 0, which makes G prime equal to 0. So something in a question would tell you this. It would either be explicit and it would say G prime equals 0, or it could just say it's a perfect dielectric. It could say the dielectric has a sigma equal to 0. It could refer to it as the insulator. It could say the insulator has 0 conductivity. It could say it's a lossless transmission line. That would also tell you that G prime equals 0. We'll see examples of all of these things though, so don't worry about it. And our last one is our C prime. We are always going to have an L prime and a C prime. But in some cases, when we deal with lossless transmission lines, our R prime and our G prime may equal 0, but you can't always assume that they equal 0. You have to be told through some means that they equal 0 before you can assume that, okay? Don't forget, epsilon equals epsilon naught times epsilon R, where epsilon R is the relative permittivity of the insulator, okay? Couple relationships here that we probably won't go into much more detail about where they come from, but you probably will if you go into ECE 571. If you go back to any of the equations we saw for L prime or C prime, for either the coax line, the 2-wire line, the parallel plate line, and you just looked at the equation for L prime, and you looked at the equation for C prime, and you multiplied them together, you'd see a whole bunch of stuff cancels, and you're just left with mu times epsilon. Okay. You do the same thing with G prime. If you divide it by the equation for C prime, you get a relationship sigma over epsilon. We won't use these too much, but we may bring it back at some point as part of a derivation. Okay. Okay, so we're going to finish off today starting an example, which I hope will drive home and, you know, put numbers to the things that we've been talking about. A coaxial line, so right there, boom, in your head, you're thinking, okay, I'm in that column on that table. I'm in like that first column, right? The coaxial line column. Inner and outer conductor diameters. I see diameters and I think to myself, okay, I can't remember which it is. If the equations have radii or diameters, but I need to be careful about it because I'm given them in terms of diameters, okay? 0.5 centimeter, 1 centimeter. Filled with an insulating material, so insulator, dielectric, that's what that means. We are told what its epsilon R is and what the insulator's conductivity sigma is. The conductors are made of copper. Calculate the line parameters at 1 gigahertz, so we're told the frequency, okay? And we are told copper properties. Sigma C, that's the conductivity of the conductor, which in this case is copper. Mu RC, so you know how mu equals mu naught times mu R? Well, if we're dealing with mu C, which is specific for the conductor, then it's mu naught times mu RC. And in this case, we're told that it equals about 1, meaning that mu C is about equal to mu naught because the mu RC is about 1. All right, so I would then flip back to my equations, my table, R prime, L prime, G prime, C prime. This is what we have to calculate, okay? All right, let's start with R prime. We'll see if we can get R prime done in the next 5 minutes, and then we'll do the rest next class. A and B, radius, radius, okay? RS, we have to use this formula. So I'll start by calculating RS, and then we'll calculate R prime. Now, one thing that I'll just emphasize here, I asked for the line parameters. That means R prime, L prime, G prime, C prime. That's the way that that collection of component values are going to be described. They're going to be called the line parameters. So if you're ever asked to calculate the line parameters, it means R prime, L prime, G prime, C prime. All right, so then let's calculate the RS. Okay, so we want RS. So what does RS equal? Well, we need our formula, which is the square root of pi F mu C divided by sigma C. So let's put some numbers to that. Pi. What's F? It's 10 to the 9, right? Because it's 1 gigahertz, 1 times 10 to the 9. Mu C, well, we said that's mu naught. And you need to know what mu naught is. You can put it on your formula sheet if you don't have it memorized. But it's a constant. It's just 4 pi times 10 to the minus 7. We need to divide that by sigma C, which is the conductivity of the copper, which is given to us, 5.8 times 10 to the 7. All right, can someone punch that into their calculator? And in the meantime, I will write our formula for R prime, which is RS, whatever it is, divided by 2 pi, 1 over A plus 1 over B. Anybody get something for that RS?
I got 0.00825.
Yeah. And that's in ohms, which is 8.25 milliohms. Pretty small number. What are A and B?
A is 0.2, 0.0,
Yes.
yeah, 0.25 centimeters.
Yep, and I'll do it in meters.
Yep.
Okay. And B is 0.5. So just remember, these are diameters. But in the equations, A and B are radii. So we have to divide them by 2, and you want to convert all the distances to meters. Okay. So we're all set then. So we have 8.25 times 10 to the minus 3 divided by 2 pi. 1 over 0.25 times 10 to the minus 2 plus 1 divided by 0.5 times 10 to the minus 2. And I'll let someone calculate that. Any questions in the meantime while someone's hopefully punching that in?
I think it's 0.07775.
0.07. Does anybody else get that? Do we have any disagreement?
0.787?
Yeah, that's what I get. 0.787, let's say, and it's ohms per meter because all of the line parameters are per meter. Okay. Okay. So we will pick it up when we come back with, we'll do the L prime, G prime, C prime next, as soon as we start on Wednesday. Any final questions about this one so far, though?
Yeah, I have one, Professor.
Yeah, go.
You know how you mentioned in the B area, it's 0.5 centimeters?
Yeah.
But look at A, it says 0.25, but over here it says 1 centimeter. Am I missing something?
Say that again. So we have the diameters. We're given the diameters, right?
Yeah, one is 0.5, which is you're
So
saying
this is
B.
this is like 2A equals that. And this is like 2B
Oh, 2.
equals that. Because
Okay.
it's giving us the diameter, but A and B are the radius.
Radiances.
Yep.
Ah.
Yep. Very
Never
common
mind.
mistake. People make it all the time.
Yeah, never mind. No, I was just trying to see where you pulled the numbers from. That's all. Never
Gotcha.
mind.
Yep. Any other questions? All right, then. I'm going to close it off. I will see you all Wednesday. We'll discuss, some procedures for and information about going back in person 1 week from today. And we'll pick up where we left off with this example. So have a good night, and I'll see you Wednesday.
Thank you, Professor.
You're
Have a
welcome.
good night.
Thanks, Professor.
Thanks. See you.